Good evening, everyone. Today I'm going to talk about space traffic management, or STM as it's typically shortened to as an acronym, which it's becoming increasingly important as the number of satellites and debris in space grows rapidly. So, with over just recently 10,000 satellites and other objects orbiting low Earth orbit, otherwise known as LEO, LEO, uh, the risk of collision and creating space fragments and space debris is higher than it's ever been. It is a very significant concern, and I will get into that later. But it for anything we need to do going to space involving satellites, going to the moon, Mars, that's even farther out. But satellites with for us basically solve so many problems. They're the reason we're connected. They're the reason we have internet. They're the reason we have GPS. They're the reason we know where things are. They're the reason why we can do excavations of these ancient civilization sites. Just going on some conspiracies there. Why we have weather patterns, how we can predict hurricanes here in Florida. It's very important because if one goes down, there could be a lot of other, and that debris is going to be moving at such a phenomenally fast rate. 17,000 miles per hour plus can hurt other things. So, what space traffic management aims to do is monitor and predict positions of those objects, the path that they're going around the globe, whichever one it is, and then use that to prevent collisions. Now, I aim to do that for long-term sustainability of space activities with AI. So, because that leads into what our to what's next here. Essentially, the problem right now is, as I've stated, over the 10,000 objects, uh, and we really need them to be safe. We need them to keep working. Okay, these satellites, like I said, do so much for us, and I have a cool graphic here showing you all of the satellites of different countries, different commercial, private, military, and whatnot. But sorry, back to the techniques. Currently, right now, if let's say Starlink sent up a satellite and they wanted to maintain it, what they would have to do, someone working under Elon Musk there at Starlink would have to get the data from the satellite um, GPS timestamp. They would get that. They would use radar data, telemetry, and essentially manually calm and filter that, which I will explain. It's fusing that data together to get the most accurate prediction. And these techniques are very outdated. They're very slow. You got to get all that data. There's a delay coming back from orbit. And then you manually at your computer at your desk have to alter that satellite's path to make sure it doesn't hit something. Now, if something's going to happen right away, like we do not have the technique right now to prevent that. Our alert system is even outdated slightly. And this leads into why AI is so important for this. I see AI's use in this field as being crucial. And as you can see here on this GIF that you see at the bottom of the screen where the guy's going through, this is all of our satellites in low Earth orbit, high Earth orbit, and middle Earth orbit. And they all have been sent up at different times. We've been sending satellites up. I believe Sputnik was the first one in 57. And it has been increasing drastically in the past 20 years. And without the use of AI in it, we will not have quick response time. We will not have the satellites have the capability to converse with each other in order to avoid each other. It's not like it's a road system, right? Like we send it up on a specific path, orbit, equatorial, and we didn't think about a Russian private phone company sending theirs up. AT&T didn't think about the new Space Forces going up or Starlinks. That just didn't happen. So that is why it's crucial. They need to talk to each other in a very efficient and timely manner without the lack of delay from the distance. And this gets me into the architecture of my project here using an AI or using AI for a data fusion system for space traffic management. So it'll collect the raw data. I got the data from Celestrak and spacetrack.org. Both of these sites are free and open use. They have all the historical data of the past 30 days of satellites. They don't have further than that because the data is it's astronomical. There are so many positions, so many satellites, as I said, over 10,000. There's a lot of data. And I just read that into the algorithm and I used other sources of historical satellite data. It wasn't just the previous 30 days. There were other countries, private, military, under certain conditions, whether it was one was under severe weather season in the northern hemisphere, one was under the southern hemisphere, etc. This was used to train the AI initially, and then base its predictions off of them. And then it should be able to make a decision on if said satellite that you are monitoring is going to collide with another satellite in the near future, or is it inevitable? Did they have to change the path now? They have to change it later. And to do this, I used a Kalman filter. And a Kalman filter, that was the name, I believe the name of the scientist who created it. What it is it takes GPS, radar, and telemetry data. So getting radar from ground-based radar in real time, the satellite telemetry data is sending up. That's what the radar is really doing. It sends it up, hits the satellite, and then it hits another satellite, so like a triangle. And when it does this, that time it took to do that, and it knows the distance away, it can judge where it'll be on the Earth. Pretty accurate. And we've been using, we use these for a lot of different things, rockets, satellites, missiles, a lot of different things. Even the new fighter jets, a lot of airplanes have these, almost everything. It's a great way to fuse data. Okay. And this was, as I was just saying, the telemetry of the ground-based radars, and that, as I said, it knows where it's at in the orbit, how far away it is. They can do some quick physics on that. Not easy, but pretty doable. And then it tries, so what the AI is trying to do then as well when it trains is filter out all the noise, all the things it doesn't need to know that it might have accidentally taken in as data. It wants to synchronize with there is a function in Python where you can use GPS timestamps for satellites. And then this is what was put in to make the AI-based fusion system. And so in doing this, I wanted this was a shorter project, so I wanted it to beat the time span of what I could do. So I used 20 epochs because to train even or any more than that from what I had researched, that would have taken too long for it to be accurate. And I think 20 even itself personally might have been too much. I probably should have started with a lower number, around 10, 5 to 10. But with this, you'll see here that over time, the model got better. You can see that over the 20 epochs, and an epoch, by the way, or an epoch, sorry, I believe I might have been saying that incorrectly. It's essentially one full pass of the data. Okay, so when you train it, when you're putting in that old data that I said to let the AI know, like giving it some background before it takes the test. Okay. And as it does this, you can see going down this list here that its loss reduces, meaning that it's getting smarter, not for every time. As I said, it's not perfect, but it gets better as so you know it's working in training. And the lower the loss, the column on the right here, the better the model is at predicting that satellite's next position. That's important because this is the time. This is how long that takes to do that. When are you getting the alert? When are we alerting, mission control? When are we alerting whoever is monitoring these systems? And that is why time is important. That is what AI is going to fix, is the time. So I did intervals over 10 minutes. Uh, I had originally tried 1 minute, but I crashed my computer. So the graph, what it'll show is its altitude at the predicted over the minutes and distance, okay, or how much it's variant. And then it'll show longitude and latitude. And what had happened after running it numerous times over the past week here, the values, just some of the data being put in wasn't being read in properly. And I personally couldn't find a solution to fix that. And the AI, I think, was working properly, but getting the documents from Celestrak and Spacetrack.org for free, they weren't formatted as well. And there's so many lines, it was hard to read them in. So here's what you will see with our data. But before that, I think I wanted to, yes, because I had mentioned about why it was unpredictable, I wanted to skip ahead to this slide because of the fluctuations and the not a number errors. These were the significant errors I received. It was either out of bounds for floating points for the ID, or it just wasn't registering as a number at all because it was outside the parameters. I'm not entirely sure at which point in the text files that this would happen when I actually had read in the last 30 days of all satellites in orbit, which is the data I used, that a couple characters were off, and then it led to a couple sections, probably about 50 satellite points being missed. And I would say probably out of, I think it was over 10,000 lines, like maybe 300 were missing, 300 to 500. But this caused the fluctuations in the predictions. And this is a perfect example of the fluctuation in the prediction. Let me move my face here. So as you can see here, the value, essentially where it's like delta, where it's moving. And what this is showing is that its longitude changed negatively, or west, and then its latitude went south. And it did this drastically over the span of about half a minute. Obviously, a satellite's not going to do that. That would be almost a UFO speed. I mean, two longitudes in that quick of a time. So, okay. Let me move this back. All right. So here are the first set of predictions. I did 3 iterations of predictions for the satellites. And the AI model, what I trained it to do is predict the longitude, the latitude, and the altitude for the next 10 minutes, as I had showed you on the future graph there. And as you can see, just going down this column right here, where you can see the values, they get out of hand. And it's about the third line where I believe the training messed up at some point. And I believe that's obvious due to this data, but these longitudinal and latitudinal values and altitudinal do not represent very realistic numbers after about halfway through. And that is why you can see that in the epochs of each iteration, you'll see right here, the third one doesn't because it produces the graph on the next slide. But these two, as you can see, it actually increases in its steps or its loss at the time it took to perform the step at the end. So what I've been working on with that is its filtering mechanisms. That was the biggest issue. The prime mechanism, what it was supposed to do, works until it gets further down the road. And these were absolutely some of the challenges that I faced. when dealing with this. Once again, this is what the third iteration produced, this chart. And we went over this. But this was some of the challenges that I faced. Uh, that it's very difficult to predict a satellite's position accurately when a human operator is not doing it. So, like, if you aren't the one actually getting that data and knowing where it is, knowing all this, there's not a good way to do that right now. There really isn't. There is a big gap in this, and AI absolutely is going to fill it. And there's a huge need for it. Something I've read through all the articles is people pushing for this for private, commercial, and military. All of them are in agreement that this is necessary. We are going to lose many things if we do not do this. So let's go over those things real quick here at the end. Why is this important? Because as I stated at the beginning, when you use your cell phone, you have Wi-Fi sending pictures of your GPS, our safety of this country, safety of anybody else's country, being able to, for maritime, to cross the sea on a boat, to fly, to go, not just to go to space, to have time be accurate across the world, for us to move money, invest in stock markets across the nation, across countries, for basically anything, for supply chain management. Everything needs this. Everything needs a GPS. Everything in this world needs to talk to each other. They absolutely need to be connected. Our global world or economy would fall without satellites. It would. We would not be able to communicate effectively across any vast distances. We wouldn't. We would go back to the mail system, which I'm sure most of us don't use as much anymore. And I think that is very crucial. It's very crucial. And so ultimately, the goal is to create a system that can provide these real-time predictions to prevent these collisions in space, contributing to this the safety and sustainability of our world. Because if that debris, if one satellite gets hit, okay, and it boom, all that debris goes up. You got to go above 17,000 miles per hour to get in orbit. That debris, all that metal, is flying at that speed. And there you saw on the previous slides how many satellites are in orbit. So you can see that would be bad. If one goes down, because there's already too much space debris in orbit, and if there's much more, we're going to see satellites being torn apart, and it's going to continue to go. We have no way to stop that. So the only way to stop it is to prevent it. Thank you for your attention. Thank you for your time. And my name is Corbin Zapp. And if you have any questions, please, this is my phone number and my email. Please do not hesitate to ask. And thank you again.